Thank you, Bai Ning, for the introduction. It's my great honor to be here to introduce our research on future of foundation models. And I will specifically focus on the revolution of model architecture for large language models. So let me start with a very quick summary of what's happening in AI in the past 3 to 5 years, and more from a technology perspective. We have seen the great success of large language models like ChatGPT and GPT-4 from OpenAI, which have fundamentally changed the AI area and even the whole industry and the human society. And the key message is that for the first time, we can train a very large and general model, which is also called foundation model or large language model, to handle all kinds of different tasks by just prompting the large language model using natural language as instructions, instead of training many small specialist models using different technology and modeling for different tasks as we have done before. And more importantly, the generalist model even outperforms the specialist model on specific tasks, especially on customization and generalization. And our recent research from Microsoft Research, as you just introduced by AJ, demonstrated that the most powerful large language model to date, which is GPT-4 from OpenAI, actually shows the sparks of artificial general intelligence, or AGI, which is a long-standing goal of AI, and a goal that no one can imagine that can be achieved in a very short time, if it can be achieved. So while it's definitely non-trivial to train such large and powerful models, the recipe to train such models is a public secret. The key ingredients is to use transformers as the model architecture or backbone network, and next token prediction or language modeling as the training objective. Then what we need to do is just scaling up the model size and the data size. Or in other words, scaling transformer is all we need. So GPT-4 is definitely a huge model. It has been reported that it contains about 2 trillion parameters and was trained with more than 10 trillion tokens. But if we compare GPT-4 with the most intelligent and successful system in our society, which is the human brain, the brain is actually 100x larger than GPT-4. Then the natural question is a scaling transformer all we need to reach the next level of intelligence, or AGI? Our answer is yes and no. So we are still seeing very positive signals by just scaling up the model size and data size. But just scaling up transformer is not enough. Here is the reason. So let's take another view of the comparison between GPT-4 and human brain. So here the x-axis is the inference cost. So even though the brain is 100x larger than GPT-4, the brain is actually 600x much more efficient. So here is just a rough estimation, and the model for GPT-4 is actually highly optimized for deployment. And this is actually the direction of just scaling up transformers, which means that we can definitely get a better performance by scaling up model size. But at the same time, the inference cost will increase even more significantly. But our goal should be here, which means the model should be large and efficient, large for performance and efficient for deployment. So we need to make the future of large language models as efficient as possible while being large, so that they can be the true basic infrastructure for human society. And it's very clear that we cannot achieve the goal by just scaling transformers. We need some fundamental research breakthroughs to make it happen. So this is actually a grand challenge and requires lots of efforts from different dimensions. And among others, we strongly believe that the revolution of model architecture will be the key foundation. So, and this will be a signal to other efforts like introducing more compute, like training longer with more tokens, collecting more data, more high-quality data, and even synthetic data as introduced by Sebastian, as eventually we will run out of data. And also the innovation and advancement from hardware and system. And actually we're seeing a very unique opportunity of co-evolution between model architecture and hardware and system innovation. So when we talk about model architecture for large language models, we have the base architecture, which is transformers, as we know. But in practice, we will also use other techniques like sparsity modeling techniques to improve the model efficiency already. So actually this is inspired by human brain, as the brain is actually very sparse. So there are two very successful techniques. The first one is called MOE, or mixture of experts. So we will introduce multiple feed-forward network in the transformer architecture, which is also called experts. Then for different input to the model, we will only activate part of the experts so that we can have a balance between model capacity and latency. And the second successful technique is called sparse attention. So we will use sparse pattern in the self-attention module in transformer, so that the model will only attend part of the context. So this will greatly improve the computation complexity for self-attention, and it's extremely important for long context modeling with long sequence as input to the model. So we specifically focus on the base architecture part. The reason is that any advancement and improvement on the base architecture can be equipped with other techniques like sparsity modeling techniques. And our research tries to push the revolution of model architecture from two very fundamental dimensions. The first one is the inference complexity. The second one is the computation precision. So for transformer, the inference complexity is ON. So here we mean the complexity to decode one token given a context. And for research, we would like to push it to limit, which is O1, as in our research on RetNet. And also we are seeing a clear trend on pushing low bit models. So we want to push it to limit, which is 1 bit, as we have done in BitNet. And RetNet and BitNet are completely complementary, so we can combine them together to have 1 bit RetNet, which we believe will be the foundation for future foundation models. So next, I will introduce a bit more details about RetNet, BitNet, but due to the time limit, I will focus more on BitNet, which is a more recent work. So here is the evolution of model architecture for large language models. So let me start with the recurrent models. Due to the nature of large language models and autoaggressive modeling, so actually RNN are great at inference, which means that it has low-cost inference. But issue with a recurrent model is about training parallelism, because it cannot support parallel training. And that's exactly why transformer was invented in 2017, so which used a self-attention mechanism to better utilize the GPU hardware and support training parallelism. And also the self-attention mechanism can have additional advantage like long dependency modeling, which means the model can actually produce even better performance. And also, more importantly, a transformer has very good scaling curve, which is super important for large language models, because eventually we need to scale up the model size. So when we talk about the new model-based architecture for large language model, we need to combine the advantage of the three goals at the same time, which means, but this is actually a very challenging task. That's why we call it the impossible triangle, which means the new architecture should have low-cost inference, training parallelism, and strong performance at the same time. And this is exactly what we have done in retentive network, or RetNet. So RetNet is the first work that makes the impossible triangle possible. So as we show in the figures, so RetNet has a great inference cost. It can greatly improve the decoding throughput, latency, and also memory consumption. And also it has strong scaling curve. And also it can support parallel training. So I will not go to the details. So you can refer to our papers for more information. And next, I will introduce more details about BitNet, which focuses on the 1-bit transformers for large language models. So here we show the training and inference weight bits of large language models. And we're seeing a clear trend on pushing low bit training and inference. And the reason is that, as shown in this figure, so the 1-bit transformer model can actually be 30x much more efficient in energy consumption than the full precision like 16-bit models. And for low-bit training, so we are actually there are some research on pushing from 16-bit like LP16 and BF16 to 8-bit training like the LP8, which was just supported by the latest NVIDIA GPU like H100. So there are lots of advantages of low-bit training, like the training speed, memory consumption. But the challenge about low-bit training is more like about the training stability. And that's why there's no much successful work on low-bit training, even for 8-bit models. And for inference, there's actually another approach, which is called the post-training quantization, which means that we can use full precision, like 16-bit in the training stage, and then we quantize the model into low-bit version, like 8-bit or 4-bit in inference. And the issue with post-training quantization is that there will be outliers in the post-training quantized models, especially for models which is larger than 6 to 7 billion. There will be emergence of outlier activations, and the performance will drop significantly for low-bit quantized models. So instead of pushing the low-bit training and inference step by step, we would like to push it to limit, which is the 1-bit training from scratch, so that we can have the advantage of low-bit training, and we do not need to quantize the model into low-bit versions, because we can directly use the 1-bit model in inference. So here is a quick summary of BitNet, which is the first 1-bit transformer that can be scaled to train 1-bit large language models. So as shown in the figures, BitNet achieves competitive performance while substantially reducing the memory footprint and energy consumption compared with state-of-the-art 8-bit quantization methods and the full precision transformer baselines. And more importantly, BitNet has a very good scaling law, which is actually very similar to the full precision transformer, which means that we can further scale up the model size to train large language models while maintain the efficiency and performance benefits. So the core of BitNet is that we introduce the BitLinear, which is as a drop-in replacement for any linear layer or linear transformation layer in transformers, including the self-attention module and also the feed-forward network module, so that we can train a 1-bit weight from scratch. So next I will introduce more details about BitLinear. So let's look at the linear transformation layer, which is a very basic component for any neural network. It's very simple. So it just maps the input activation X to the output activation Y using a very simple matrix multiplication. But if we use the same model architecture to train low-bit models, like 1-bit in RetNet, there will be a training stability issue, as I just mentioned. So even for very small size models, like 100 million parameters, the large language model training will diverge very easily for 1-bit vanilla transformers. And that's why we have the key design principle of BitNet, which is stable training. And to achieve the goal, so we first introduce a layer norm to preserve the variance of the activations. So this is actually very similar to our work on which is very similar to sublayer norm as we introduced in DeepNet and Magneto, which focus to fundamentally improve the training stability for large and deep transformers. And then we will quantize the activations into low-bit versions using aka.ms quantization. So this will ensure there will be no outliers in inference because we do it the same way as in training. And then we will recover and scale the precision of the output. So this is actually very simple but effective. And all the components here are very essential to guarantee the training stability of BitNet. So as mentioned, the RetNet and BitNet can be combined together, which means we can use the bit linear layer, as I just mentioned, to replace the linear transformation layer in RetNet, similar as we have done in transformers. And we have some preliminary experiments shows that actually BitNet works very well with RetNet as well. So which means we believe that the one-bit RetNet will be the foundation architecture for future large language models. So to summarize, we envision the future of foundation models to be simply large and efficient. Large for performance and efficient for deployment. So the first problem has been almost solved by the scaling law, and we are working on solving the second problem by the evolution of model architecture. And we believe our research on RetNet and BitNet will be the key foundation to achieve the goal. So moving forward, we strongly suggest that we should work on scaling one-bit RetNet instead of scaling up transformers, but we can actually combine with other techniques like the sparse modeling techniques so that we can make sure that the future of large language models to be the true basic infrastructure for everyone. So in addition to the research on model architecture, we have done lots of pioneer research on pushing the evolution of multimodal large language model. And particularly, our research on VALL-E, which enables large language models to speak naturally like human, and our research on Kosmos 1 enables large language model to perceive or see, and to ground between language and vision, as we have done in Kosmos 2, and also to support a general capability of iterating, as in Kosmos 2.5, and also to generate image in context, as we have done in Kosmos G. So we have shared all the links here. So if you are interested in our work, so you can refer to the papers for more details. So last but not least, we'll share more information of our work through this link. And this ends my presentation. Thank you.